the definition of anti-unitary operation is also given. So an anti-unitary operator is very much like the unitary operator, but with a lot of more complex conjugations. So first, it's not a linear operator. It's an antilinear operation. By antilinear operation, we mean when U acts on this linear combination of the vectors, we cannot just simply pull out the coefficients C1 and C2. When we do that, we have to also add a complex conjugation to C1 and C2. This is the definition of part of the definition of the operation. So from your linear algebra class, this kind of thing doesn't happen if U is a matrix and possesses a vector. Indeed, here U is not a simple matrix. It cannot be just represented as a matrix. This is antilinearity, and then in order for antilinear operation to be anti-unitary, we further demand under this operation, the inner product will take a complex conjugation. Next, so yes.
What is the Hermitian of U?
What is the Hermitian conjugate of U?
Yeah. Of the anti-unitary.
That depends on your definition. You can define it. You can still define it using the matrix elements.
U is not a matrix.
Yeah, we can talk. We will discuss this in more detail. So in the lecture today, we will only talk about the unitary operations. In week 7, which is the week after the next week we have no class. You know that, right?
Yes.
Then on September 30th, we will have the midterm exam. That's the Tuesday. Then on Thursday, we will talk about the anti-unitary symmetries in more detail. Although U is not a matrix, you can still ask. You can still ask something like this. This is what I mean by the matrix element. This is still something you can define, and then you can, based on this, you can define a complex conjugation. We will talk more about that later. But for that, what's more important is really not the complex conjugation. It's not the Hermitian conjugation, but the inverse of the anti-unitary symmetry. In fact, for unitary symmetry, what's important is also the inverse. It just happens that for unitary operations, the inverse is the Hermitian conjugation. Okay, so don't worry about the anti-unitary operator for this lecture. We will talk about it more systematically in 2 weeks. But you do need to use it in problem 3 of assignment 5. Sorry, I've been sick since last week. Yeah, but I think in assignment 5 you have enough hints to do it. Okay, so in both cases here, the absolute squared of 2 vectors doesn't change. No matter whether we take the complex conjugation, this equation still holds because we are taking the absolute square. You see here, this is the left-hand side is the probability. Let's look at the right-hand side first. This is the probability for the original state psi 1 to collapse into the state psi 2, right? And here, this is the probability for the state u psi 1 to collapse into the state u psi 2. In fact, if we demand this hold in general, then that's how Wigler showed that all these invertible symmetries must be either unitary or anti-unitary. Any questions about the statement here? The meaning of the statement? Okay, let me make a remark. It's important to know that here we are talking about invertible symmetries. Nowadays, in fact, starting from about 2018 or 2019, there's a new research area called non-invertible symmetries. It's very young, just starting from 2018, 2019, and now it becomes a very big research area. Non-invertible symmetries. They are not unitary or anti-unitary operators. Those symmetries, I have to say, they are still not fully understood, and it's a very active research field. In our class, we will not touch upon it, but you are welcome to take a look. Okay, let's look at some examples of the unitary operations. Suppose we consider a single qubit. We have seen many examples of the unitary operators, like this operation x. The operator x is a unitary operator, right? Because x times x dagger is identity. X dagger is x, and x squared is identity. So the same happens to y and z. This you can all check this, right? What about this one? Why is this a unitary symmetry? Is this obvious to you? Sorry, why is this a unitary operator? Is this obvious to you? Yeah, very good. So as we reviewed in week 1, unitary operators can always be written as e to the I times some Hermitian operators, and any e to the I times some Hermitian operators is also a unitary operator. Actually, they're just the same thing. So you see, what is appearing here is a Hermitian operator. Therefore, exponential of that is a unitary operator. Now, if we have multiple qubits, then these terms are unitaries. First, for these two, you can easily check. Take the dagger and multiply it by itself, we get identity. And for this one, we can use this criteria that this is exponential I times some Hermitian operator. Okay, and here this is a unitary for the same reason. This is a Hermitian operator. And here, again, this is a Hermitian operator in the exponential. So exponential I times that is a unitary operator. This holds for both bosons and fermions. Any questions here? Okay. Okay, then these are unitary operators. Now we need to know how these unitary operations really act on states and on operators. It's natural that we say a unitary U acts on state in this way instead of opposite becomes U dagger opposite, right? Then this will demand that the operator had better be acting this way, because operator can be written as an outer product of the states. These operators, you see, this operator can always be written as this. So if the states are acting like that, then the operator should be acting in U and U dagger in this particular order. So let's look at some examples. Again, for a single qubit, we have the basis state 0 and 1, and consider the x unitary. X axon 0 gives 1, axon 1 gives 0. That's just based on the definition for x. Then when it acts on the operators, you see, if it acts on x, x will be transformed into this operator, and this is equal to x. If it acts on y, y will be transformed into this operator, and this is equal to minus y. Are you familiar with this fact? X, y, x dagger is equal to minus y. We can check this. So x is this one, y is this one, and x dagger is also this one. And you can check this is equal to minus y. And the same for z. As another example, let's consider 2 qubits. And this is the unitary operator we want to examine. So, for example, if we want to act on this state 0, 0, then x1, z2 acting on 0, 0 will give us 1, 0 because x1 acting on 0 will give me 1, and the z2 acting on the second 0 will just give me 0. Yeah.
So, Professor, the lecture note is that for the dagger in front, that is the dagger or I'm just curious.
Lecture notes?
Yeah, on campus. But you dagger or
I changed it. That was an older version. I need to update it.
So it's U or U dagger.
Yeah, in this convention it's U or U dagger. But this turns out to be not that important. I will not bother you with whether it's U or U dagger or U dagger or U. You will see this doesn't really matter for our applications. Yeah, good question. So as you know, U and U dagger, they are inverse of each other. So the physical difference is one of them, if one of them is rotating by 90 degrees in this direction, the other is rotating by negative 90 degrees. Just that. But you know, as long as later you will see, as long as rotating by 90 degrees is a symmetry, rotating by 90 degrees in the other direction is also symmetry. So it really doesn't matter. Yeah, this we can check here. If I consider this, you want to call this U, right? Yeah, and indeed, in this example, this U acting on this operator will be x plus a. And in this case, when you put U dagger on the left, it has the same effect as that. But I don't think it really matters. Maybe let me clarify this point. So here, when we define the operations on the operator, we can consider what kind of standard we need to use. There are 2 standards. In one standard, we can say, suppose we calculate any expectation value. We demand either the operation acts on the states or the operation acts on the operators, but the expectation value doesn't change. So we demand this, which is the expectation value after we transform the state. We demand this to be the same as this, where O prime is the operator after the transformation. If we demand this, then O prime would be U dagger or U. This is one way we can define it. Another way we can define it is to say, now I don't demand this. Instead, I demand for all my states in my system, I just change all my states. I just change all my states in this way. And then all the operators they will just follow the change of the states. These are just the two different definitions. You can take either one. I don't think it matters too much. It makes no difference in real applications. Their meanings are different, but ultimately for important things it doesn't matter. But there the equations are all clearly stated.
Sorry?
There the equations are all clearly stated. The meaning should be clear there. Okay, any other questions? Okay, if we look at the action of x1, z2 on 0, 1, then x1 acting on 0, the first 0 gives 1, and z2 acting on the second 1 gives -1. And that's why we get this one. If we look at this action on the states, you can also verify it in this way. Maybe one lesson we want to extract here is if we have a string of such Pauli operators, then if we have two strings of Pauli operators, then they either commute or anti-commute. This is something that's good to keep in mind. It will simplify a lot of calculations. Further question here?
So let's say we apply the unitary operator, let's say x, y, x dagger equals to minus y. How do you, is it able to tell from first glance that this is true?
Is there a way to tell what?
Y, x dagger is minus y.
Why is it -1?
That's why we got there, right?
Yeah, you see, one way to justify this to use the matrix. Huh?
You have to do calculation to prove it?
Yeah.
Or,
This is combination of 1x, so we have x goes to
so the n type of
x and y have to be
okay.
Yeah. But to show that they anti-commute, you need to do a calculation. Any further questions? Okay. Let's just play this game for some examples. So consider bosons or fermions and act this operator to this operator, this unitary to these operators. Let's see what is the resulting operator, and acting this unitary to this state. What is the resulting state? think I said something wrong just now. If I take this as u, if I take this thing as u, what's appearing here is not x plus a, but x minus a. So you see, in this definition, if I call this u and this u dagger
Why is it minus?
so P1 is minus I h bar derivative. So minus I P1 over h bar a would be minus a derivative, right? This will give the minus.